Okay, so today's great meeting, we have David Long. So David Long is a graduate of the group. He did honors and masters with me in the distant past. He is mainly these days working on topics in condensed matter physics that are nonetheless close to, in some form, topological error correction, I suppose. He did his PhD in Boston. He's been at the University of Maryland as a postdoc for the last year. He's about to start at Stanford. All information you could have gotten from the slide. And he's going to talk about this work, which is collaboration with Dominic Aus, who maybe, there's generational change. So Dominic also did his honors and masters in the group at an even earlier phase, and these days is a promoter. Okay, thanks very much, David. Take it away.
Even I didn't overlap with Dominic else here.
Yeah, right. even you are not far enough in the distant past. Yeah.
Okay, so I'm going to be talking about a particular classification of topological phases, in particular these localized topological phases. And I'm going to more or less take a mostly condensed matter perspective, but I will try to give some intuition or some relationship between what I'm going to be talking about and a more quantum information perspective, in particular in terms of error correction. So from a condensed matter perspective, why might one want to do a topological classification of localized systems which kind of don't transport particles, for instance, or don't transport some kind of conserves quantity across the bulk. The reason is because this property of localization turns out to be pretty robust in systems which are strongly disordered, so systems which have a lot of spatial inhomogeneity. So if you do a topological classification of these systems, basically asking what localized systems can I deform into one another without going through some kind of phase transition, then you can hope that this is associated with kind of robust properties that can be used for various applications, or can describe something maybe in the natural world. So of course, the big example that everyone knows is the integer quantum Hall effect, which is nowadays used as a resistance standard, right? Because these plateaus of the Hall resistance in the integer quantum Hall effect is so precisely quantized. You can use that as kind of a benchmark, what the ohm is in your lab. So we could also hope to get some kind of technological application like that out of these localized phases. So there's a much older classification of ground states, which is kind of much better developed. It's not complete in all dimensions, but it's somehow much better explored. And I'm going to be particularly emphasizing the role of these anomalous localized topological phases, which are exactly the localized phases which are kind of outside of that classification of ground states. And so you need to know more than what has been done in previous literature to understand these anomalous localized topological phases, which I will henceforth abbreviate as alt phases, both because that's the acronym and also maybe to emphasize that these aren't your grandma's exotic topological phase. Okay, so kind of the main message about these alt phases is going to be that these are phases which are non-trivial, even though their ground states are non-trivial. So they have no eigenstate order, it's said. If you look at any individual eigenstate, you can deform that state to a product state and live in a trivial phase. But these, the whole entire Hamiltonian nonetheless cannot be deformed to some kind of atomic insulator without going through some kind of delocalization transition. So that's stated here, you can have trivial eigenstates but still have a non-trivial Hamiltonian, or the contrapositive of that statement, you can have a non-trivial Hamiltonian but nonetheless have trivial eigenstates. And this is precisely realized by these alt phases. And okay, more than just saying that these things exist, which is something which has more or less been implicit already in the literature. Dom and I actually managed to do the classification of these things for spin systems. And it turns out that there's some relationship with these so-called quantum cellular automata, or QCA, which are just like locality preserving unitary maps. And furthermore, we can like augment this classification with all your favorite adjectives, provided that your favorite adjectives belong to this list of 4 things. Okay, so I'll start by talking about localization, because I appreciate there's no net matter group. So first of all, delocalization, like presumably it's familiar that if you have like a periodic, like translationally invariant potential, then there's some like translation operator which commutes with the Hamiltonian, and you can simultaneously diagonalize the translation operator and the Hamiltonian. So as to say that like there's a momentum associated to the eigenstate solutions of the Hamiltonian, and that means that these eigenstate solutions need to be these like extended plane waves. So that if you have a periodic potential, then you have these delocalized eigenstates, these things which are spread out. And correspondingly, if you like sit a particle in this kind of potential here, then most of the time, like except in fine-tuned cases, it will kind of spread out across the entire system. On the other hand, if you have strong spatial inhomogeneity, so if you have some potential that like looks like this kind of mess, then if this disorder is strong enough, if these like wells are deep enough, then the low energy states of this system become these exponentially localized things. So if you like start a particle in this well, then like it's not actually going to be able to tunnel into like arbitrarily distant sites. It's going to like remain kind of exponentially confined near here. And in fact, in one dimension for single particles, you don't even need like strong disorder. It happens at any kind of strength of disorder. You can like add some like tiny sprinkling of dirt and everything just suddenly becomes localized, at least asymptotically. And so, you know, how you could describe this is that you can say that like in some like spectral decomposition of the Hamiltonian, I write it as like a sum of eigenvalues times projectors onto the eigenstates in this kind of like single particle picture. And those projectors onto these single particle states are going to be like local operators, right? They're just these things which like live on small sections. And this kind of presentation more or less generalizes to the many body context. So I'm not just talking about single particles, but I'm talking about a system of perhaps many particles. But so now the projectors on the eigenstates, it's like hard to talk about any kind of notion of locality on those things, like is a projection onto like the all zero state or local operator. But nonetheless, you can talk about these other like local integrals of motion, which also commute with the Hamiltonian. I'm going to write these things as like tau operators with superscript z, so tau z. These things commute with the Hamiltonian, and they're kind of like the analogous objects of these like localized projectors onto these single particle states. But now they're many body operators in this like interacting system.
But what kind of do you assume a certain kind of interactions?
No. So if you have like strong enough disorder, in the sense of like have like a part of the Hamiltonian which consists of like commuting terms, which could just be like the occupation of this site, and those come with coefficients which are like large and random over some large range, then this is like the generic scenario that you will at least for very long times, there's an effective description of the Hamiltonian where you have these emergent local integrals of motion. And it's often presented as kind of like a definition of many body localization that like such things exist. And at least, yeah, at the very least, at like every order of perturbation theory, a decomposition like this is like robust to kind of a generic local perturbation. So I won't have to specify a particular form of
it's robust to a kind of interaction. Is that
any
kind of interaction?
Any kind of local interaction. Yeah. I mean, like of course you can write down like strong perturbations of the Hamiltonian, which are no longer local, but like, yeah.
And the J here is as a spatial, it's saying where you're located in space.
Yeah. Yeah, and so for nice enough like local integrals of motion that are like in some sense maximal. Now this means that the Hamiltonian is actually going to decompose into something which is a sum of these local integrals of motion, and then like higher order terms where I have like products of local integrals of motion.
So sorry, what is a local integral of motion?
So it's an integral of motion because it commutes with the Hamiltonian. It's local because it's some, yeah, it's some like exponentially decaying sum of operators which are supported only on a few sites. Okay, and so like the thing to notice is that for these localized systems, like at the end of the day, like what the characterization was that the Hamiltonian is going to be a sum of commuting terms, right? So there is this non-obvious basis, which like is not just like the bare basis of like single sites, in which we can write the Hamiltonian as a term in terms of like a sum of these commuting local integrals of motion. So by a classification of localized systems at like a more kind of like mathematical level, what I'm talking about is a classification of like commuting projector models, if you want. This is like Hamiltonians, which are sums of commuting terms. And while the property of like being a sum of commuting terms sounds like very fine-tuned, the argument is that with this like strong disorder, actually it's not very fine-tuned. You can make a slight perturbation to the Hamiltonian, and at least at like any kind of like timescale accessible to perturbation theory, you will continue to behave like you're in a sum of commuting terms. So it's not as fine-tuned as it sounds. Okay, I will also be talking somewhat about systems with driving. So this is where the Hamiltonian depends on time. I'm going to be particularly talking about quasi-periodic driving, of which like periodic driving, it's okay, is a subset. So I'm saying that the Hamiltonian depends on time through some like periodic phase variables, right? So like theta 1, theta 2, 3, 4. And there are these like quasi-energy states, basically these like time-dependent projectors, which also like are conserved, right? In the sense that these like local integrals of motion were conserved. So for the many body version, it's that saying that there are now explicitly time-dependent local integrals of motion, which like in the Heisenberg picture are conserved.
Meaning they commute with the Hamiltonian at that time.
No, meaning that that like
Yeah, right.
The like total time derivative of tau in the Heisenberg picture is 0.
Yeah. So that means the mean value of tau is actually not changing with time.
Yeah. So in the Heisenberg picture, they are static operators. So if I start with some initial state, which is, you know, has a definite eigenvalue of all the tau operators, then I just like go through some quasi-periodic family. It's like theta family of states. Okay, and in particular, like the expectation value of this operator indeed remains constant at all times. So yeah, you can kind of think of this as being like the occupation of some like local mode, right? Like the kind of picture of these like many-body localized systems is that like up to some dressing, or in this case, up to some like time-dependent dressing of the state, they basically look like collections of product states. Okay. Okay, but like the property of being a collection of product states already allows for like a bunch of non-trivial things to happen. The first of which is going to be this eigenstate order, which I talked about, kind of a property of like the eigenstates of these localized systems. So in particular, like what's going to be useful is that localization is a property which is not just about the ground state, it's a property about the entire spectrum. And so you can really talk about like non-equilibrium systems as being localized and having like impact from that. So without localization, with like systems like this, the energy spectrum might look something like this. It could have like a gap ground state, and then it's got some like low excited states, and then eventually like in most cases, you'll end up in some kind of continuous spectrum at high energies. And so it can happen that you can have kind of order in the ground state, right? You could have like a ferromagnet or something which some kind of interesting, or like, for instance, like topological order in the ground state. But these highly excited states are more or less going to look just like thermal states. So they can still be ordered for like symmetry breaking, but they won't have like topological order, and like kind of rightly or wrongly, these things are sometimes described as being featureless. It's just to say that they look like thermal states for these highly excited states. So if you're like very far from equilibrium, right? If you're like sitting in some eigenstate or some like small collection of eigenstates at a very high energy, then you are actually not going to generically have like any more order than you would expect in like a classical system. On the other hand, if you have a localized system, then the ground state is going to be some like simultaneous eigenstate of all these local integrals of motion, right? All these like commuting projectors in the commuting projector description of the Hamiltonian. So that state for sure can have some kind of order, like it could be like a ferromagnet or a paramagnet. It could have some kind of topological order. Of course, like the toric code that may be familiar is a commuting projector Hamiltonian, so it supports topological order. But then all these highly excited states are also just simultaneous eigenstates of these commuting projectors. So these highly excited states can also support different kinds of order. So they can also break symmetry. They can also have topological order. So this is called eigenstate order, like the fact that like even if you're like extremely far from equilibrium, these like highly excited states can still support the same kind of order as a ground state has in like a delocalized system. So this was like been known for like maybe a decade now, and it tells you something about like the classification of localized topological phases. So what do I mean by that? I'm going to think about drawing some kind of generic phase diagram, right? So I'm going to like pick out like any number of parameters that can occur in my Hamiltonian, and so in particular, like the most generic phase diagram I could draw would consist of like every parameter that can occur in a local Hamiltonian. So I'm going to have some big kind of schematic gray box here, which consists of all local Hamiltonians. And out of this, I'm going to pay attention to some particular collection of these, which is consisting of localized Hamiltonians, right? These things which maybe in some emergent basis look like commuting projector models. So here they are in these white circles. And you'll notice that like each of these, that this like is divided into like several different patches, right? So it means that if I have a Hamiltonian which lives in this circle and a Hamiltonian which lives in this circle, then these things are separated by a phase transition, right? So like I can't go from this Hamiltonian to this Hamiltonian without the localization length diverging in this system. So I can pick out one of these Hamiltonians and identify it as like a trivial Hamiltonian. This will be like some like atomic insulator, right? So in a qubit system, I could just say it's like a sum of sigma z's. It's like single qubit commuting operators with disjoint support. And then I could call this phase the trivial phase, right? It's the collection of all Hamiltonians which can be deformed to this like trivial Hamiltonian. And so any kind of property which is characteristic of this entire collection is going to be the same here as for this trivial Hamiltonian. Whereas it could be the case that maybe some other collection of these things has some other like different kind of properties. Could have like a magnetization for symmetry breaking Hamiltonians, or it could have some kind of topological order in these excited states. And so by seeing that there's some kind of eigenstate order, this like symmetry breaking or like topological order, I can see that I can't be connected to the trivial phase because if I were, then I would be able to like deform this topologically ordered state into the trivial state, which I cannot do. But while this is some like evidence that you have something which is not in the trivial phase, it is not like a necessary condition, right? There's one of these things which I like haven't colored in as being like some kind of eigenstate ordered phase, and like this can happen, right? These are the phases which I want to call these alt phases. These are localized phases, which I cannot connect to the atomic insulator, but for which there is no particular kind of eigenstate order. That means if I look at the eigenstates of this system, I could deform them to product states. I could deform them to like the eigenstates of this Hamiltonian, but I cannot deform the entire Hamiltonian at once. Like I can't deform the entire spectrum to the spectrum of this atomic insulator without going through a delocalization transition. And so this can be accompanied by like different like quantized observables taking different values, like here.
David, is it clear that there's just one such like phase and that you can deform all of them to each other?
It's not. No, like there's many more than just like these four things, right? And there are many anomalous phases. Yeah, there are going to be like countably many. Yeah, so there are many. Okay, so at this point I'll try and like make an aside to like make a comparison to error correction. So like certainly the first time like I encountered like topological phases was in the context of error correction in like the toric code. And so I think it like helps to like put this in that context, like given the interests of the group. So first of all, maybe I don't need to recall like what is an error correcting code. Completely generally, like not saying anything about like stabilizers. An error correcting code is a subspace of Hilbert space, right? So if I'm trying to encode a qubit in some quantum system, I just pick out a logical 0 and a logical 1, and that's my error correcting code. And like most of the time, this is not going to be a very good code, right? It's going to be hard to decode. It's going to, I mean, if I pick things bad, it'll be very susceptible to errors. But like this is like a definition of an error correcting code. So for instance, the repetition code defined in this way, I could say that my logical 0 state is like the all 0 states for some chain of qubits, which maybe I could represent as like up arrows. And the logical 1 state is some chain of 1 states, which I represent as down arrows. And this is my code space. So you can think about like trying to like classify these error correcting codes, but without any additional structure. All codes of the same dimension are the same, right? Because I just like rotate any subspace of Hilbert space into any other subspace of Hilbert space. So maybe you can make it like a restriction into like the class of subspaces, which I'm going to consider, which is like much more restrictive. Should be, I'm saying that the code space has to occur as like the ground space of some local Hamiltonian in whatever like system which I'm considering. So this is kind of like the classification of ground states in condensed matter systems, if you like make this restriction. On the other hand, a stabilizer code is like one particular example of a construction of error correcting codes, where you say that your code space is achieved as a simultaneous eigenspace of a collection of stabilizers, which I've kind of suggestively written as being tau z, indexed by some number j. And so, for instance, the repetition code is such an example, right? You can take your stabilizers to be this collection of operators for this chain of 4 qubits. But this means that if I were to like think about the corresponding Hamiltonian for this thing, then my Hamiltonian is not going to be like a completely generic local Hamiltonian. It's going to be something which is a sum of commuting terms, right? So this is more like the classification of localized Hamiltonians, which I've been talking about. So I think one way to understand this like distinction between like classifications of ground states, classification of localized systems in the error correction context, is that it's distinguishing between kind of equivalence of codes at the level of like just like subspaces of Hilbert space, an equivalence of codes at the level of stabilizers, right? Like saying, I can put that a little bit more precisely. I can say that like codes are equivalent if there's some like finite depth circuit, which I've written here to be finite, which relates like this ground state, this ground space to the other ground space. And this is like the classification of ground states. But I can say that stabilizer codes are equivalent if I can like conjugate the stabilizers of one with some finite depth circuit and get the stabilizers of the other. And these things are not the same. These related to the classification of localized systems. These things are not the same, both because like not all codes of this kind can be achieved as stabilizer codes, but also because even if you have two stabilizer codes which have the same ground space, they can be inequivalent. And that's like an example of these, because of the existence basically of these alt phases. Or rather of phases which are not characterized only by their ground states. So for the rest of the talk, I'm going to be focusing on these alt phases. And to give full disclosure, alt phases are bad codes because they have no eigenstate order, so in particular, they have no topological order. So they have to generate, they have like unique ground states and so don't function as codes. But the condensed matter point of view, they're kind of already interesting because they can have like quantized observables. And they're kind of a starting point for like building like a bigger theory, which includes things with like topological order. So I can, oh yeah, and the kind of like driven things which I was talking about, I believe, like people in this group know this better than I do, are related to these like dynamic codes, where the stabilizer group evolves with time. So for instance, like I'm thinking of these like Floquet codes, where like there are the instantaneous stabilizers, which are like periodic in time. That would be like these Floquet or these like periodically driven localized phases. Okay, so I'm going to give kind of at least like a phenomenological picture of a particular example, which people have known about for some time. I guess it's these papers. It's like where this phrase anomalous comes from, which is this so-called anomalous Floquet phase. So it's a two-dimensional system with a periodic drive. It doesn't matter whether I talk about like fermions, bosons, interacting, non-interacting. These things kind of all work the same for this phase. And this phase, just in terms of like what it does, rather than a particular model, in the bulk, it has these fully localized circulating states. So these like local integrals of motion can just be like single site operators, which kind of like hop around in little loops in the system. And on the edge, there's some quantized current. So at the edge, rather than these local integral motion, local operators kind of circulating, they instead kind of run along the edge. So phenomenologically, it's pretty similar to like a Chern insulator or like an integer quantum Hall effect, where in the bulk you have some kind of like magnetization if these particles carry charge, and on the edge you have this current associated, which is like quantized and associated to like the bulk phase. And so how I want to think of this is in terms of a kind of bulk boundary correspondence between this like Floquet phase in the bulk and some kind of like thing that happens on the edge after you've done like one periodic cycle of the drive. And so I want to think of this in terms of pumping some kind of operation across the system. So specifically, I want to say that it's like pumping a translation from one edge to the other, right? So here, after one cycle, we do like a translation to the right on the top, and a translation to the left on the bottom. And I want to think of this as like taking a translation to the left away from the top edge and like putting it on the bottom edge. So we do a translation to the left on the bottom, and we take a translation from to the left away from the top, so that does the translation to the right. And this is a kind of picture that will turn out to generalize.
Sorry, do your local integrals of motion go around the edge as well? Because you said they, like, when you drive it with the pump in the bulk, your local integrals of motion are doing little like
Right.
loops, but around the edge, do you get like one local integral of motion that goes all the way around?
Yeah, so maybe like to clarify, like the local integrals of motion for these like topological systems like exist and like are periodic in the bulk.
Yeah.
If you took like the equivalent operator in this system and like followed it along the edge, indeed it would like kind of like go all around. Which actually tells you that like the edge is not localized, right? Like if I start like a particle here, then like it's going to move.
Right.
So like localization for these systems is a property of the bulk,
Not the boundary.
not the boundary. And so then when you put it on like open boundary conditions, you can like fail to continue to be localized at the edge. Yep. Okay, and it turns out that these bulk eigenstates can be deformed to product states. Maybe that's easiest to say, it's like the single particle picture, right? Like I said, that like your individual eigenstate is just this thing which tracks a particle, which kind of like moves in a circle. And it's not hard to deform like a path of eigenstates, which moves in a circle to just a path of eigenstates, which is just like at a single point for the entire cycle. But it's not possible to do that for all eigenstates simultaneously in the bulk. Kind of to do this, you have to like move some of this circulation of this state into like the surrounding eigenstates to like keep the entire thing unitary. So it turns out that if you like kind of coarse grain on a sufficiently large scale, the magnetization density of this bulk is quantized. So while individual eigenstates can be deformed to like trivial states, the entire system cannot be deformed to an atomic insulator. So this is an example of an alt phase. Okay, and so what's the relationship to these quantum cellular automata or QCA? It's actually like pretty simple. Like a QCA is a locality preserving unitary, so it's any kind of unitary map which takes local operators to local operators, which is supported like close to the original ones. So in particular, I'm going to consider the map V, which takes kind of like the microscopic physical degrees of freedom. So in this like single particle thing, it could just be like the state consisting of like the projector onto the state consisting of the particle like just at this position. And this V is going to map that state to some associated eigenstate of the Hamiltonian, right? So one of the local integrals of motion, one of these like projectors onto the onto the eigenstates for the particle case. And because I assumed that these states are localized, then this is indeed a locality preserving map. And so this is the QCA I want to associate to like the Hamiltonian with these eigenstates. And you can do something similar for the many body case. Now just like qubit systems, I can think about the unitary V, which maps Pauli operators to these tau operators, one of which is this like tau z, the local integrals of motion. So these are local. And such a V exists whenever basically you can find an associated tau x to these tau z's. I would like to say that that's basically true in systems which have like so-called short-range entanglement. I kind of present it as a definition for what short-range entanglement means for localized systems. One can show that any eigenstate of a Hamiltonian, like with this property that like it has a tau x as well as a tau z, is short-range entangled in the usual sense. And I believe that the converse is true, but cannot prove it. So it means that it's kind of like, certainly if it's completely equivalent, then it would be like a sensible notion of saying that like Hamiltonians with this property, like are short-range entanglement in the same way that we used to for states.
So just so I understand, so the point you're making here is it's not just that these local integrals of motion exist and diagonalize the Hamiltonian, but if I want to flip the value of one of them, I can do that by acting locally.
Exactly. Yeah.
Right.
Yep. So yeah, indeed, like this condition has appeared elsewhere in the literature under the name of local flippability.
Right. And so that would generally rule out topologically ordered systems where I can't locally flip a single stabilizer.
And you can show that like anything with like ground space degeneracy that with like protected ground space degeneracy, like is gonna not meet this condition. But it's also insufficient. Like you can't just say that unique eigenstates is enough, because you could think about the toric code on a sphere, which has unique eigenstates, but which also fails this condition. Okay, so this V is going to be the locality preserving unitary, or the QCA, that I associate to like a given Hamiltonian. And you can also think about time-dependent V's for these like time-dependent systems, where this V is now going to be like a periodic function of time. Okay, and I claim that if you can deform one of these V's associated to some localized Hamiltonian to a V for some other localized Hamiltonian, which kind of live in this kind of decomposition of the Hamiltonian, then you can deform the Hamiltonians into one another. It's relatively straightforward. You just take the V naught here, you deform it into V1, and as you do this, you take the kind of coefficients in this, like the eigenvalues, and you deform them to the new eigenvalues, and this takes you from this Hamiltonian, that Hamiltonian. So it kind of tells you that there's some relationship between the connected components of these QCAs in D dimensions, which I write as I0 QCAD, and these like static localized phases characterized by these localized Hamiltonians that look like this. So there's some redundancy in this description, right? Like there's like a map from like I0 QCAD to like static localized phases. But the redundancy is easy to characterize. It's just like permutations of the sites. So there's a QCA, which is translation, which is not the same. It's not possible to connect the identity QCA, but clearly if I take an atomic insulator and I like translate all the stabilizers, I get the same set of stabilizers. So that's obviously like not encoding anything useful. And it turns out that that's basically the complete redundancy. Yeah, and so I also talked about these families of UCAs, like time-dependent ones, for driven systems. And so for those, we're not talking about connected components of QCAs, but rather like homotopy classes of maps from some like torus of these drive phases, right? So like the phase associated to each of the periodic drives that we're driving the system with, in maps from that into the space of QCAs. Okay, but like basically it means that this is motivation to like fill out a table of all of the homotopy groups of these QCAs. And if we can like fill out some table like this, then it's telling us that like, this is a sufficiently powerful formalism that, we can like answer questions about like localized phases in these kind of like different dimensions and with different like numbers of drives. Okay, so we can like go and consult math literature and see like how much of this table has already been filled out by other people. So there are some. So pi0 of QCA1, right? So like connected components of QCAs in one dimension were classified some time ago. They have a log rational classification, which is maybe already telling you this is like not going to be so simple. But actually, like it's kind of like a scary presentation of like a relatively simple thing. Basically, like all the non-trivial QCAs in 1D are translations. but it just turns out that like a translation of a qubit is like not deformable to a translation of a qubit, right? Like a 3-level system. So like you have like a different integer index for like all prime dimension qubits. And so there's some way of like parameterizing that in terms of like the log of a rational number. And even in terms of just a rational number if you want, I took the log just to make the group operation addition. Okay, so there's some like not finitely generated set of connected components of QCAs in 1D. And so we can hope that maybe the maths literature has already filled out more of this table, done a little bit. Actually, this is a result from Williamson and co-authors, who was here until relatively recently, I think. So it turns out that in 2D, there is a nice group. It's the trivial group. There are no non-trivial QCAs in 2D. In 3D, we don't know the full classification, but various people have like worked out at least like, I guess, 16 non-trivial examples in 3D. And this basically takes us up to like the status of the literature before our paper. So out of infinitely many elements in this table, we have managed to fill in 2 plus epsilon. And we have infinitely many left to go. Okay, but actually like there is another part of this table which is easy to fill in, which is 0 dimensions, right? That's just like unitary matrices. And people know a lot about unitary matrices. So you can work out like what is the classification of these things, even all the like higher homotopy groups. They turn out to be trivial in even degree. For most odd degrees, there's like a rational classification again. This is again like some kind of like pathology related to like this one. There's like an integer classification in any like finite qubit system, but then you want to like talk about systems of all sizes simultaneously, and you end up with some rational classification. And then because like strictly speaking, these things are projective unitaries, not unitaries, there's actually like a Q on Z, Q on Z classification in 1D. So this is like U1 phases with like rational exponent. And that's just because like you're regarding unitaries which differ by a global phase being the same unitary.
And you said 1D just now, but what you actually mean is number of drives on 0 dimensions.
Yes, sorry. That's like loops of QCAs in 0 dimensions. Okay, so I guess that was a big step forward, right? We filled in like infinitely many elements of this table. Unfortunately, you know, the nature of infinity, we still have infinitely many left to go. So how do we fill in like the rest of this table? And so how you can do it is you can use this bulk boundary correspondence, which I talked about in terms of the anomalous Localized phase. So this turns out to like work for like all dimensions and even like higher homotopy groups. So like the picture is that, like, let me just say it first for Fouquet phases for like loops of QCAs. The picture is that in some like bulk, like infinite system, I have like a loop of QCAs which begins and ends with the identity. And I'll put that on open boundary conditions. So I need to like modify the Hamiltonian at the edges so that I can like not couple across that edge anymore. And so in general, I'm going to do something non-trivial at the boundary. And the bulk, I still begin and end at the identity because there's like a finite range of this QCA. And I'm like, you know, more than that range away from the edge. But at the edge, like, you know, within some distance from the edge, I can do something non-trivial. And so I can either describe the system in terms of like the loop of things I did in the bulk, or in terms of like the discrete thing I did at the edge at the end of this loop. And the claim is, and you can like argue with some degree of success, that this is like an isomorphism, right? That like this entire loop in the bulk is characterized by just like what you did at the edge. So for this anomalous Fouquet phase, like the point of view is that, like, you know, there are in 1D, there is this translation QCA. And so this 2D loop of QCAs I can view as arising from this like 1D translation at the edge. And actually this, yeah, they said you can do this actually for all the homotopy groups. So the nth homotopy group of QCAs in D dimension, you can think about, like, you know, going through like one of the variables and looking at what like the n-1 variables that are left did at the edge. And this also is an isomorphism.
Sorry, just so D here is the spatial dimension.
Spatial dimension is like,
and N is the number of drives. Right.
Yeah. So you can use this relationship two ways. Like either you can do it maybe like how I presented it here, right? Like I have this like 2D phase and I want to like understand it. So I look at the edge, or that's kind of like a deductive reasoning, or you can use it like inductively. You can say, well, I know that there is this 2D phase with one drive. And so this has to be something which occurs at the edge of some 3D phase with two drives. So we can make a prediction from this like bulk boundary correspondence that there has to be this 3D localized phase with two drives, for which the edge response of this thing is going to be the bulk response of this thing, right? So there's some 3D phase with like a bulk with an edge magnetization, which is quantized, which is kind of like viewed as like pumping this thing to its edge, like through every cycle of this like omega-2.
So your pi 1 of QCA with D equals 2 is like the closed loop, right?
Yep.
In the surface. What does pi 2 of QCA 2 look like?
So I can show you a full table. So the condition I wrote down on the previous slide basically means that this table is constant along diagonals. So let's look at it. Pi 2 of two-dimensional QCAs is trivial. So that's a sphere of QCAs with like, you know, one of those points in the QCA being the identity. And then the claim is that like any such sphere you can deform into a point again in 2D. Right. But if you were to look at some like 3 sphere, then that would no longer be true.
Right. But isn't the fundamental group of any sphere greater than 2 trivial? Like, why do you get the 3 sphere? You get Q mod Z.
So you're talking about homotopy groups of spheres, right? Like I'm talking about like maps, homotopy classes of maps from spheres into QCA.
Right.
Right. So like you're talking about IN S.
Yeah. Which is related but different.
Yeah, I mean, like it's a homotopy group of a different space. Okay. So this indeed is trivial for like n less than b. Whereas this is not. This is some completely different space with like totally different homotopy groups. Like this is like. Yeah, like this is saying like, you know, there's some like space of QCAs which like, you know, I don't know how to draw, but then through this like, you know, algebraic constructions, you can say like some things about like the shape of this space in the sense of like, you know, if I have a sphere and I'm like mapping it into here,
right?
Like what spheres can I form into another? So it's basically saying that like this like QCA2 has no like co-dimension to like holes in it, right?
Yeah. So you just end up getting the nice loops for pi 1 QCA2.
Yeah. So pi 1 is always going to be like loops, like like co-dimension 1 holes in this space, and there is such a hole. In fact, there are many such holes for two-dimensional QCAs. And there are also such holes for zero-dimensional QCAs. And then the higher than that, it becomes kind of speculative. But yeah, like that's like kind of what the goal of like algebraic topology is, right? Like you don't know exactly what this space is. It's like kind of hard to imagine, but you can like do algebra and learn things about the shape of that space in terms of these like numbers of holes.
I know that this is just like an extension of what exists, right? But do you expect that the difference, if the difference between the number of drives and the dimension is even, that you'll always get like a trivial space?
It's a good question. I don't know. Yeah, I know. I don't know of any reason why that should be true. In like sufficiently high dimensions.
Because like obviously the reason it like happens is just because you've taken the zero-dimensional case and then this is like easier to show, right? And then that just extends for like the huge swathes of the table. But then obviously after like these high dimensional things are unknown.
I guess it's like already possible to show that this is true in like all physical dimensions, right? That like D less than
Sure.
based on like what results people have already shown. But then like it would also require that like all four-dimensional QCAs are equivalent, and I don't know if that's true. Okay, so I can wrap up very quickly. This is like the classification of QCAs. I said that like the translations all prepare the same localized phase. So if you're talking about classification of localized phases, like some of these like don't count. So that one's not real, that one's not real. But all the rest of these turn out to be real localized phases, and in fact alt phases. Let me skip this slide. There's a way to say when something is an alt phase, and if you apply that test to the elements of this table, actually like all the non-trivial things which I wrote like are alt phases. So while for like spin systems without symmetry, there are no like ground state phases of localized models. These are commuting projector models. It turns out that there are many alt phases, including ones in like static systems. Okay, so that takes me to the end of the talk. Main message again was that there are these alt phases potentially related to like classifications of like stabilizer codes, which have trivial eigenstates, but which themselves are non-trivial in the sense that they can't be deformed to an atomic insulator. And more than that, like we managed to like do the full classification, including for like driven systems. And I didn't talk about symmetry, but we can do that too. Thank you.
Cool. Thanks very much. Are there more questions? No, I mean, we had a number of questions during the thing. So so does this settle? So you've, well, if for all physical dimensions, including with symmetry, you could argue that this settles the problem. What's kind of left open for?
Is the
Okay, this one's not settled.
Yeah, right.
But in terms of what's left open, I think that the thing that we're most interested in is the case with topological order. So these were these like short-range entangled phases, which have like unique ground states and like are bad for error correction, for instance. It somehow becomes much more difficult as soon as you start wanting to talk about like models with anyons or something.
Yeah,
models which like good error correcting codes. So that's something which we're working on now, and it's like IDU is kind of like the major next step.
Cool. Brilliant. I think we're pretty much on time. Thanks.